Hello dear students, today is the fifth lecture for our course Probability Theory. Today we will talk about independent random variables. In real life, we usually need to deal with more than one random variable. For example, if you study physical characteristics of people in a certain area, you might pick a person at random and then look at his or her weight, height, and so on. The weight of the randomly chosen person is one random variable, while his or her height is another one. Not only do we need to study each random variable separately, but also we need to consider if there is dependence between them. Is it true that a taller person is more likely to be heavier or not? The issues of dependence between several random variables will be studied in detail later on. But here we would like to talk about a special scenario where two random variables are independent. The concept of independent random variables is very similar to independent events. Remember, two events A and B are independent if we have probability of A intersection B equal probability A times probability B. Remember, comma means and or intersection. Similarly, we have the following definition for independent discrete random variables. Consider two discrete random variables x and y. We say that x and y are independent if probability x equal x and y equal y equal probability x times probability y for all x and y. In general, if two random variables are independent, then you can write probability of x element in A, y element in B equal probability x element in A times probability y element in B for all sets A and B. If two random variables x and y are independent, if knowing the value of one of them doesn't change the probabilities for the other one. In other words, if x and y are independent, we can write probability y equal small y, given that x equal small x equal probability of y for all x and y. Similar to independent events, it is sometimes easy to argue that two random variables are independent simply because they don't have any physical interactions with each other. Here is a simple example. If you toss a coin 2n times, let x be the number of heads that you observe in the first n coin tosses and let y be the number of heads that you observe in the second n coin tosses. Since x and y are the result of independent coin tosses, the two random variables x and y are independent. On the other hand, in other scenario, it might be more complicated to show whether two random variables are independent. If you toss a coin twice and define x to be the number of heads you observe, then you toss the coin 2 more times and define y to be the number of heads that you observe this time. Find the probability of x less than 2 and y greater than 1. Since x and y are the result of different independent coin tosses, the two random variables x and y are independent. Also note that both random variables have the distribution we found in the previous example, we can write probability of x less than 2 and y greater than 1, which is equal to probability of x for 0 plus probability of x for 1 times the probability of y for 2, which is equal to 1 over 4 plus 1 over 2 times 1 over 4, which is equal to 3 over 16. We can extend the definition of the independence to n random variables. Consider n discrete random variables x1, x2, x3 until xn. We say that x1, x2, x3 until xn are independent if the probability for x1 equals small x1, x2 equals small x2 until xn equals small xn equal to probability of x1 times the probability of x2 times the probability of x until xn for all x1, x2 until xn. Special distributions. As it turns out, there are some specific distributions that are used over and over in practice. Thus, they have been given special names. There is a random experiment behind each of these distributions, since these random experiments model a lot of real-life phenomena. These special distributions are used frequently in different applications. That's why they have been given a name, and we devote a section to study them. We will provide BMF for all of these special random variables, but rather than trying to memorize the BMF, you should understand the random experiment behind each of them. If you understand the random experiments, you can simply derive the BMF when you need them. Although it might seem that there are a lot of formulas in this section, there are in fact very few new concepts. Don't get animated by the large number of formulas. Look at each distribution as a practice problem on discrete random variables. The first distribution is Bernoulli distribution. What is the simplest discrete random variable that you can imagine? My answer to this question is a BMF that is non-zero at only one point. For example, if you define probability of x 1 for x equal 1, 0 otherwise, then x is a discrete random variable that can only take one value, which is x equal 1, with a probability of 1. But this is not a very interesting distribution because it is not actually random. Then you might ask, what is the next simplest discrete distribution? And my answer to that is the Bernoulli distribution. A Bernoulli random variable is a random variable that can only take two possible values, usually 0 and 1. This random variable models random experiments that have two possible outcomes, sometimes referred to as success and failure. Here are some examples. You take pass and fail exam. You either pass, resulting in x equal 1, or fail, resulting in x equal 0. You toss a coin. The outcome is either heads or tails. A child is born, the gender is either a male or female. Formally, the Bernoulli distribution is defined as follows. A random variable x is said to be a Bernoulli random variable with parameter b, shown as x distributed as Bernoulli b if its BMF is given by probability x equal b for x equal 1 minus b for x equal 0 otherwise, where b is between 0 and 1. And the following figure shows the BMF of Bernoulli random variable. A Bernoulli random variable is associated with a certain event A. If event A occurs, for example, if you pass the test, then x equal 1, otherwise x equal 0. For this reason, the Bernoulli random variable is also called the indicator random variable. In particular, the indicator random variable IA for an event A is defined by IA equal 1 if the event A occurs, 0 otherwise. The indicator random variable for an event A has Bernoulli distribution with parameter b equal probability of A, so we can write indicator A is distributed as Bernoulli b of A. The second distribution is geometric distribution. The random experiment behind the geometric distribution is as follows. Suppose that I have a coin with probability h equal b. If you toss the coin until you observe the first head, we define x as the total number of coin tosses in this experiment. Then x is said to have a geometric distribution with parameter b. In other words, you can think of this experiment as repeating independent Bernoulli trials until observing the first success. This is exactly the same distribution that we saw in example 3.4. The range of x here is 1, 2, 3 and so on. In example 3.4, we obtained probability x for k equal probability x equal k equal 1 minus b with power k minus 1 times b for k equal 1, 2, 3 and so on. We usually define q equal 1 minus b, so we can write b of x or probability of x for k equal b times q with power k minus 1 for k equal 1, 2, 3 and so on, to say that a random variable has geometric distribution with parameter b. We write x distributed as geometric b. More formally, we have the following definition. A random variable x is said to be a geometric random variable with parameter b, shown as x distributed as geometric b if its probability function is given by probability x for k equal b times 1 minus b with power k minus 1 for k equal 1, 2, 3 and so on, 0 otherwise, where b is between 0 and 1. The following figure show the probability function for geometric 0.3 random variable. We should know that some books define geometric random variables differently. They define the geometric random variable x as the total number of failures before observing the first success. By this definition, the range of x is r of x equal 0, 1, 2, and so on, and the probability function is bx for k equal b times 1 minus b with power k for k equals 0, 1, 2, 3, and so on. In this book, whenever we write x is distributed as geometric with parameter b, we always mean x as the total number of trials as defined in the definition 3.5. Note that as long as you are consistent in your analysis, it doesn't matter which define or which you use or which definition you use. That is why we emphasize that you should understand how to derive probability function for these random variables rather than memorizing them. The third distribution is binomial distribution. The random experiment behind the binomial distribution is as follows. Suppose that you have a coin with probability of head equal b. If you toss the coin n times and define x to be the total number of heads that you observe, then x is binomial with parameter n and b, and we write x is distributed as binomial n and b. The range of x in this case is equal to 0, 1, 2 until n. As we have seen in section 2.1.3, the probability function of x in this case is given by binomial formula, which is probability x for k equal n combination k b with power k 1 minus b with power n minus k for k equal 0, 1, and 2 until n. We have the following definition. Random variable x is said to be binomial random variable with parameters n and b, shown as x distributed as binomial n and b if its probability function is given by probability x for k equal combination n combination k times b with power k times 1 minus b with power n minus k for k equal 0, 1, 2 until n, 0 otherwise, and b is between 0 and 1. Figures 3.4 and 3.5 show the binomial n and b probability function for n equal 10 and b equal 0.3 and n equal 20 and b equal 0.6 respectively. Binomial random variable is the sum of Bernoulli random variables. Here is a useful way of thinking about binomial random variable. Note that a binomial n and b random variable can be obtained by n independent coin tosses. If we think of each coin toss as a Bernoulli b random variable, the binomial n and b random variable is the sum of n independent Bernoulli b random variables. This is stated more precisely in the following lemma. If x1, x2 until xn are independent Bernoulli B random variables, then the random variable x defined by x equal x1 plus x2 until xn has binomial NB distribution. To generate a random variable x distributed as binomial n and b, we can toss a coin n times and count the number of heads. Counting the number of heads is exactly the same as finding x1 plus x2 plus until xn, where each xi is equal to 1 if the corresponding coin toss results in heads and 0 otherwise. This interpretation of binomial random variables is sometimes very helpful. Let's look at an example. Let x is distributed as binomial n and b, and y is binomial m and b. Be two independent random variables. Define a new random variable as z equal x plus y. Find the probability function of z. Since x is distributed as binomial n and b, we can think of x as the number of heads in n independent coin tosses. We can write x equal x1 plus x2 until xn, where the xi's are independent Bernoulli B random variables. Similarly, since y is distributed as binomial m and b, we can think of y as the number of heads in m independent coin tosses. We can write y equal y1 plus y2 and so on until ym, where the yj's are independent Bernoulli B random variables. Thus, the random variable z equal x plus y will be the total number of heads n plus m independent coin tosses. Z will be equal x plus y, which is equal to x1 plus x2 until xn plus y1 plus y2 until ym, where the xi's and yj's are independent Bernoulli B random variables. Thus, by lemma 3.1, z is a binomial random variable with parameters m plus n and b. Therefore, the probability function of z is probability of z for k will be equal to m plus n combination k times b with power k times 1 minus b with power m plus n minus k for k equal to 0, 1 and 2 until m plus n, 0 otherwise. The above solution is elegant and simple, but we may also want to directly obtain the probability function of z using probability rules. Here is another method to solve example 3.7. First, we note that the range of z equal 0, 1 and 2 until m plus n. For k is element in range of z, we can write probability of z for k equal probability of z equal k equal probability of x plus y equal k. We will find that the probability of x plus y equal k by using conditioning and the law of total probability. In particular, we can write probability of z for k equal probability of x plus y equal k, which is equal to summation from I equal 0 to n for the probability of y equal k minus I times the probability of x equal I, which is equal finally to m plus n combination k times the probability of k probability times b with power k times 1 minus b with power m plus n minus k. Thus we have proved z is distributed as binomial m plus n and b by directly finding the probability function of z. Thank you, and we will continue the negative binomial distribution in the next lecture.